Okay, this is kind of going to be a little bit odd, but we'll see how it works. Um, I'm trying to do a lesson on 1.3 from home. I'm doing it using an airliner, which is kind of a tablet, and I haven't used these in years, so we'll see how it goes. I'm just going to do a little practice right here. Uh, we'll see how it goes. That wasn't too bad. 1.3 looks at applications of transformation of systems of equations. You've seen a lot of these. You know, you've all taken algebra 1 and algebra 2 and all that, and so you've seen a little bit. Um, Mostly, it's kind of where the two lines intersect and linear representations. I want to look at two different videos today. The first one is kind of curve fitting, polynomial fitting. So that's what I'm going to call this. I'm going to say this is a polynomial fitting. And you've kind of seen this before. I know for a fact that everybody has seen if I give you 2 points, then you can create one line. Um, that's pretty basic stuff right there. And of course, if I give you 3 points, oops, I don't want to do that. Let's delete. And let's go ahead and delete all this crap. I give you 3 points. You should have learned in pre-calculus or algebra 2 that you can get one parabola, and so on and so forth. I mean, if you get 4 points, then you can create a cubic function. And really, the idea is that if you're given n points, then you can create an n minus 1 degree polynomial. And so that's what I want to look at today, is using linear equations, systems of equations to do this. So let's start with an example. We'll call this example 1. It's in the book somewhere. I might have just made this one up. I can't remember. Let me give you the points. 1, 4, 2, 0, and 3, 12. So obviously we should be able to come up with some parabola based on these points. I'll just plot them right here. 1, 4 is about right there. 2, 0 is right around there. That area. 3, 12 is around there. So it looks to me like this is going to be parabola. It looks something, maybe like that. I'm not really sure. There's no real way of knowing, but it is going to be a parabola. And more than likely it's going to have a positive lead coefficient. So what I want to do here is I'm going to say what is a parabola first off. Well, a parabola is an equation p of x equals some constant plus some first degree term plus some second degree term. That's basically the idea. Oops, not. I need to erase that. Let's see if I can figure out these. That's very nice. Some second degree term. And so what you want to do is you want to systematically plug in, like this right here will be an x, and this right here will be a p of x. So to plug in all three of those. So the first equation I'm going to get is I'm going to get a0 plus 1 times a1 is a1 plus 1 squared is also 1, so a2 equals the p of that x is going to be 4. In the second equation, if I plug in the point 2, 0 is going to be, well, a0 is going to stay the same, plus 2 a1 plus, I gotta square it now, 4 a2 equals, in this case, equals 0. And then the third one is going to be a0 plus 3 a1 plus 9 a2 equals 12. And from there, you can kind of see our coefficients become our variables in this case. And you can kind of tell that every parabola is going to have an x and going to have an x squared. And really, the only thing that differentiates between the two is the coefficients between each one. All parabolas take on this form. We just want to figure out what is each coefficient so that it goes through these points. So I'll make an augmented matrix where the coefficients actually are the variables. So this is going to be 1, 1, 1, 4, 1, 2, 4, 0, 1, 3, 9, 12. I'm not going to write out every step. We've done all this a couple times now. So I got 1, 1, 1, 4. This comes to 0, so multiply by negative 1. Negative 1 plus 2 is 1, that's nice. Negative 1 and 4 is 3. Negative 4 and 0 is negative 4. 0, negative 1 and 3 makes 2. Negative 1 and 9 makes 8. Negative 4 and 12 also makes 8. Now you can get rid of that 2, so 1, 1, 1, 4. 0, 1, 3, negative 4, 0. I'm multiplying by negative 2 now, so that becomes a 2, positive 8, and positive 8 is 16. And so it looks to me like the final answer is going to be, let's see here, this is the A2 column, so get that 2A2 equals 16, so A2 equals 8. I get that A1 plus 3A2, that's 24, equals negative 4, so A1 equals 28. And the last one, of course, A0, A0 plus 28. Did I make a mistake somewhere here? I feel like I must have... A1 is negative 28. I just made a mistake just right there. Let's make this, let's just get rid of all that. So it's A0 minus 28 plus 8 equals 4. So A0 minus 20 equals 4. So A0 is 24, which means our polynomial, which is kind of what they wanted in the end anyway, is going to be 24 minus 28x plus 8x squared. There's your parabola that goes through the point. So that's not too bad. You can kind of see how, because I'll do one more of those. How long have I been recording for? 8 minutes. I want to try to keep this to under 25. This will be example 2. I'll go a little bit faster here. For one of the points, negative 1, 3, 0, 0, 1, 1, and 458. And this might be just good practice for everybody. I'm just going to kind of skip some steps here. I know that the polynomial has got to look like, well, it's 4 points, so it should be a third degree. So it's A0 plus A1x plus A2x2 x squared plus A3x cubed. So that's the polynomial we're looking at. So my first one is going to use the point negative 1, 3. So this is a 1, x is negative 1, x squared is 1, x cubed is negative 1, and the solution is 3. This is still 1. There's no x's with this. So this is always going to have a 1 out in front no matter what x gets plugged in. And then the rest of it's just straight up with zeros for the second row. 0, 0, 0, 0. And then I got 1, so that's pretty easy. 1, 1, 1, 1, 1. And the last one's got, it's kind of a pain. I got 1, 4, 4 squared is 16, 64, and then 58. And so I'll slide down a little bit. See if we can't solve this guy. So I got 1, negative 1, 1, negative 1, 3. Multiply my negative 1 to get 0, positive 1, negative 1, positive 1, negative 3. Multiply by negative 1 again, so we get 0, 1 and 1 make 2, negative 1 and 1 make 0, 1 and 1 make 2, negative 3 and 1 make negative 2. And then I got 0 here multiplying by negative 1 again, so that's 5, 15, 65, and 55. Well, that bottom row, that looks like I can work with that. I don't know. Let's just get rid of these. Make this 5 a 1. Make this 15 a 3. Make the 65 a 13. And make the 55 an 11. Just for convenience sake. Let's extend the page a little bit. Now I got 1, negative 1, 1, negative 1, 3. This stays 0, 1, negative 1, 1, negative 3. This is going to become a 0. This is a 0. So multiply by negative 2, so that becomes 2. That becomes a 0. 6 and negative 2 is 4. 0, 0. Multiply by negative 1, so that becomes a 4. Negative 1 and 13 is 12. And positive 4, positive 3 and 11 is 14. Which means the last one is pretty easy. I might even be able to slide it right in here. Got a 1, a negative 1, a 1, a negative 1, and a 3. I got a 0, 1, negative 1, 1, negative 3. A 0, a 0, a 2, a 0, and a 4. And then last we have a 0, a 0, a 0. Multiplied by negative 2. That says 12, negative 8, and 14 is 6. Just to put everything up here. It looks to me like A3 is going to be a half. A2 is going to be 2. And then I got A1 minus 2 plus a half equals negative 3. So, let's see, add the 2. So I get negative 1. So A1 is negative 3 halves. And then A naught, the last one. Got A naught plus 3 halves, so plus 1.5 plus, is that right? A1 plus 1 negative 3 halves, that's right. Plus 2 minus 0.5 is supposed to equal 3. So I get 3.5, 3, yeah, A naught equals 0. So the polynomial that I wanted is going to be the polynomial, let's see here, P of X. Nothing for A naught. A1 was negative 3 halves, so negative 3 halves X plus A2, which is 2, X squared plus 1 half X cubed. And there's your polynomial. Now obviously what you can do is do this much, much, much faster on a computer. And you can see how computers fit those curves. You just take a series of points and then create a 5th degree, 7th degree, 8th degree. Microsoft Excel is very, very fast at this. That's kind of how it works. So that's an example. Okay, that's actually number 4 out of your book. So just kind of to look at it up later on if you want. I wanted to keep this recording under 20 minutes. I got 5 minutes left. Excuse me. Let's see here. All right, the next one I want to look at is number 16 out of your book. This might be the last one I look at with you guys. Number 16 out of your book says, which gives you the sales model. So let's go ahead and look at this. We'll call it example 3. It gives you these sale models from Walmart in billions of dollars. That's a lot of money. So it gives you kind of this chart. It's like in the year 2000, they did $191.3 billion. Good grief, that's a lot of money. 2001, they did 217.8 billion. 2002, they did 244.5. And 2003, they did 256.3. And then there's more. It goes up to 2007. It might not be enough for him. 2004, they did 285.2. In 2005, they did 312.4. In 2006, they did 346.5. And in 2007, they did $377 billion. So they're doing pretty well. It looks to me like they're almost a linear growth rate there, maybe even worse. Anyway, this is obviously the year, and this is the number of dollars in billions for Walmart. And they wanted to, the question on 16 says, use the dates for 01, 03, 05, and 07, so all the odd years, to come up with a cubic polynomial, to come up with a cubic model. Now, I didn't do this out by hand for obvious reasons, but I want to show you how to use technology to get this done a little bit faster. First off, you don't want to use 2001. You just want to use the number 1. So basically, what I'm going to do is kind of a transformation. I'm going to let z equal, x minus 2000. So when I use 2001, yes, x equals 2001, but z equals just 1. And so my equation is now going to be p of z. And so it's going to be a naught plus a1x, or I'm sorry, z, plus a2z squared plus a3 z cubed. And so the first year, of course, is 2001. That's going to be, the p of z is going to be, how much did they make in 2001? 217.8. So that's going to be, a naught is still going to be a naught plus 1. I'm using z as 1. So a1 plus 1 squared is still 1, so a2. 1 cubed is still 1, so a3 equals 191.3. Oh, I'm sorry, that's not right. 217.8. 217.8. And so then the next one would be z equals 3. So that's going to be a naught plus 3a1 plus dot 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 dot. I'm not going to keep going with this. I wanted to focus now more on actually using some technology here. to get this problem solved pretty quickly without even uh, not even a calculator. About 20 minutes yet. Yeah. What I did was I went to Google and I put online row echelon form and I put transforming a matrix to row echelon form. So the number of rows, well, if I look at my matrix here, it looks to me like I'm going to have a row for every year. So that's 1, 2, 3, 4 rows. So 4 rows and 5 columns. And I'll submit that now. And then it comes up like this. And the first row, if you remember, was all ones. 1, 1, 1, 1. Second row was 2003, so that's 1, oops, 3. 3 squared is 9. And then 27. And then I'm leaving that last one out. And then 1, 5, 25. And then 125. And then 1, 7, 49, 49, 343, and 72. Now I gotta go back and I gotta type in this, the other ones. So it's 217.8, 217.8, it's 6, isn't it? 8. And then in 2003, they made 256.3. 256.3. And then it's 312.4. And then the last one was 377. So, and then I just hit submit. Now, what happens here is error. It says make sure all entries are integers or fractions. No decimals allowed. Now I've already gone and put them all in the fraction mode by using a fraction calculator. So you can kind of see, when I do this, it's going to be like 1,089 divided by 5. Done. And this one is like 205563 over 10. And this one is 1,562 over 5. And now that I put them all in fractions, we'll hit submit. And this is where it gets really nice. Not only does it give you the answer at the bottom, but it shows you exactly how you would transform that matrix into a row echelon form. And it just, you slow you all the way down till it's the very bottom. And you can see they do a really nice job. They actually put it in reduced row echelon form. So you can kind of see this one right here. There's your answer. I mean, that's your cubic polynomial right there. Very, very ugly, but it works. You can test it to make sure it goes through all those points. So that's kind of a nice tool. It's math.odu. I guess it's Old Dominion University. So that's that. That's kind of the basic way to do it. I want to finish on this now for this video. It says, this is 16b. It says solve the system, which we did. And then, does the solution produce a reasonable model for predicting future sales? And the answer is no. I mean, the answer is a resounding no. Polynomials do not model things that we use very well. Because of the fact that polynomials go off into space. They go up to infinity. They have continual growth. They don't level off at all. They just kind of go all the way up or all the way down. And so that's not really a good model. Let's say this, it's good points close to 2007. But the model predicts infinite sales as time increases without bounds. That's ridiculous. Things will level off. So typically polynomials are great. They're easy to work with, but a logarithmic model where things kind of would level off or would kind of find a happy medium will be better. or an exponential model. Obviously, logarithmic is an inverse of an exponential model. So don't think that this polynomial fitting is the be all and end all. It's a great, great, great tool, but obviously it doesn't work for everything because most populations, everything in the long run does level off, which polynomials don't do. Um, so I think that's it for now. Your homework, I'll probably post online, so don't worry about that. Did I break 25 minutes? Yeah.